my name is Munmun Mohanty. I am a PhD student working with Professor Parimal Parag, Department of ECE, and today I'm going to talk about my work on data center network transport protocols. Now, a data center network is critical infrastructure for service providers to store data and make decisions. Data center networks consist of a large number of compute and storage nodes interconnected through high bandwidth network switches and links. A substantial fraction of these data center network traffic comprises of short messages, which require very low latency, and long message, which require high bandwidth. Transport control protocol, which has been around for the last 40 years, it isn't appropriate for this kind of setting. So we need new transport protocols which can accommodate the requirements of modern data center networks. Now, there are modern transport protocols like HOMA and Data Center Parallel Iterative Matching or DCPM protocol, which ensure low latency and high utilization by using priority queues. Like you can see this figure, it depicts the general setting of a data center network where the links in the core are high bandwidth, but the links at the edge, like the downlink over here, they are of lower bandwidth. So the bottleneck we need to take care is at the edge switch. Now, how do these protocols handle this? So at a high level, these protocols, the edge switch, it divides the buffers. It takes care of this issue by having two buffers, one for short messages and the other for long messages. So you can think that these protocols address these issues by allowing transmission of short messages with high priority, and long messages are transmitted only if the sender receiver pair are matched and the short flow buffer is empty. Then what is our goal here? The existing protocols, they have demonstrated their results empirically. We aim to analyze and model the protocol that will help us in performance comparison and suggest modifications for an improved version. However, the analysis of these protocols is difficult in the most general case. So under certain assumptions, we model the downlink from edge switch to receiver as a discrete time queuing system and derive the expressions for performance metrics like flow completion time and throughput. Now, the transmission phase generally of these kind of protocols consist of two phases, the matching phase and the data transmission phase. In matching phase, the problem of finding a conflict-free sender-receiver pairing is equivalent to that of a bipartite matching problem. In data transmission phase, long message packets are sent in slots where there are no short messages. So like you can see here, as an example, sender 1 has a long message packet for receiver. It can send it in the time slots where there are no short messages. As soon as there is a short message from some other sender, the long message packet transmission is paused and resumed only after short message has been transmitted. So we validate our model by comparing the analytical results with empirical results. As you can see here, this plot, they are the results for a 60 cross 60 setting where there are 60 senders and 60 receivers. The transmission phase length of their transmission phase length is some 40 maximum transmission units. The short flow size is 8 maximum transmission units, and long flow size ranges between 400 to 500 maximum transmission units. We compared the mean throughput obtained theoretically and empirically for these 60 hosts as a function of increasing number of short flows per phase, and as expected, with increasing number of short flows, the throughput decreases. And here we have found an upper bound, analytically we have found an upper bound on the throughput. Thank you.